Chapter 12, Section 7 in the 8th grade textbook is entitled Solving Systems of Linear Equations by Graphing. So, let's get some clarity here on what we're talking about, because that title alone might have confused some people, and I can understand that. What is a system of equations? System of equations is two or more equations in the same problem, basically. Okay? Two equations with two variables each, x and y. Solving a system of equations can be done in a lot of different ways. Graphing to solve systems of equations is just one of those ways. When you're solving a system of equations in any way, whether it's by graphing or with a method that requires calculation, what you're doing is you're finding a value for x and y that will work in both or all of the equations that you're given. Sometimes you can find an x and a y that works in just one of the equations, but you can't always find a set that works in both equations without some work. And that's what this method is about. Now, there's a downside. The downside to solving systems of linear equations by graphing is you have to make really nice graphs. You have to be really, really precise. Because if you're not, you're going to come up with the wrong answer. The reason that's going to happen here is because when you solve a system of linear equations by graphing, you're going to end up with two different lines on the same coordinate grid. To find the solution to the system of equations, you have to tell me at what point do my two graphs intersect. One precise point. Sometimes it's really easy. They go through nice perfect grid markers and it's done deal. Sometimes they don't. It's when they don't that we run into problems. Because unless we've drawn our lines really, really nicely with straight edges or rulers, chances are what's going to happen is we're going to have a hard time discerning, is it halfway through a grid box or a quarter of a way through a grid box, and that can really skew your answers. So what you're going to have to spend time on here is attending to precision, making sure that not only you come up with the right graph here, but then that you also graph it really, really neatly. Now, as far as the graphing procedure here, I can give you equations in any single way I want. I can give you something in point-slope form. I can give you something in standard form. I could give you something in slope-intercept form. I could give you something that used table method form. It doesn't matter. You can graph it any single way you want. If it's in form, graph it with form. You want to do the table method for everything, do the table method for everything. But what's important here is when you want to solve the system, you've got to tell me at what point, x comma y on the coordinate grid, do those two graphs intersect. Alright, and with that introduction out of the way, let's go ahead and take a look at the first example here. It says a fishing boat leaves the harbor traveling east at 16 knots. Knots are simply a term that describes nautical miles per hour. After it travels 40 nautical miles, Coast Guard cutter follows the boat traveling at 26 knots. After how many hours will the Coast Guard cutter catch up with the fishing boat? Okay, so two equations here. They've decided to let t be time and d be distance. Now that's a little bit of a problem for us because when we're graphing in the coordinate grid, we need things to be x and y because that's always how we graph, because that's all the coordinate grid shows us, x and y. So one of the first things we're going to do here is we're going to change all these graphs into something that are x and y. But for now, we're going to work with what it says here. All right, so t is going to be time, d is going to be distance. Start off with the fishing boat. Write an equation that describes where the fishing boat is at the end of this scenario. Well, remember, what does it say here compared to the Coast Guard cutter ship? After it's gone 14 miles, it's still traveling at 16 knots. So that's why they wrote 16t plus 40. Right? 16 knots times however long it travels plus the 40 nautical miles is going to be wherever it's at in that distance and time. All right, since it's in miles per hour, nautical miles per hour, all right, T represents a time in hours. So if I'm talking about 1 hour later, okay, it's already gone the 40 miles, and then it's going to go the other 16 miles, 56 miles. We'll look at the equation, 16t plus 40. If t is 1, 16 times 1 is 16, plus 40 is 56. Exactly what I just said. If it's 2 hours out, 16 times 2 is 32, plus 40 is 72. The boat is 72 miles out. Makes sense. 16 knots, 2 hours, all right, that's 32, plus the 40 it was already out, 72. All right, if it goes 3 hours out, 16 times 3 plus 40. It's already 40 miles out, and then it's gone 16 3 times over. 40 plus 16 plus 16 plus 16, or 16 times 3. We do the math there, that's the same as 48 plus 40, or 88. Okay? We don't know how many hours out this boat is. Could be 1, could be 2, could be 3, could be 3.75, could be 5.5, we don't know. So instead of doing 16 times 1, or 16 times 2, or 16 times 3, they're doing 16 times t. Now, Coast Guard ship, it's starting at ground zero. Right? It's just trying to catch up to that other boat. Right? It's just traveling at 26 knots. Again, it hasn't gone anywhere yet. So the equation there is going to be d equals 26t. 26 times how many ever hours it's out is going to equal the distance it's out. Right? Now that we have that, now we're supposed to graph each equation. And then, again, because the point of intersection is what's important here, all right, we're going to go ahead and identify that point of intersection. Now, let's go ahead and take a look at this one here. Again, we want to change these to x and y's. I know d and t are important here, but our coordinate grid doesn't have d and t on it. Our coordinate grid has x and y on it. So we're going to go ahead and change those to x's and y's, just for the purpose of graphing. We can erase them in a second through the magic of the whiteboard, and that's exactly what we'll do. Okay, now, as far as graphing these, again, you can graph these in any way you want. I want to graph these in slope-intercept form. Start off with this fishing boat, 16x plus 40. The number at the end here tells me the intercept, the y-intercept of this line, 40. So I put a dot at 40. Then my slope here is 16. Slope of 16, remember, is the same as 16 over 1. So from this point, I'm going to go up 16 and right 1, put a dot. And you can keep going up 16 and right 1, up 16 and right 1, up 16 and right 1 as many times as you need to. All right, and we'll connect those points with the line. Now, I'm going to do this one with slope-intercept form too. Now, some of you might be looking at that and going, well, wait a minute. That's missing something. If I remember slope-intercept form right, if what you just showed me is true, slope-intercept form has to be y equals mx plus b form. But that's missing the b at the end. So how can you do slope-intercept form? Well, that's a good question. All right, if I want to make this go into slope-intercept form, all I'm going to do is add one little thing on the end of this equation that doesn't change anything, plus 0. All right? Well, you already know that adding 0 to any number, anything, doesn't change it. If I do 3 plus 0, it's still 3. If I do 5 plus 0, it's still 5. If I do x plus 0, it's still x. Same thing here. Adding 0 doesn't change anything. But now it's in slope-intercept form, and now I can make a graph. So the y-intercept point here is 0, dot at 0. And then my slope here is 26, which again, write it as a fraction, 26 over 1. So I'm going to go up 26, right 1, put a dot. Up 26, right 1, put another dot. Up 26, right 1, put another dot. And keep going. All right, now in this particular question, they kept doing that over and over and over again. Because what happened here is when we did that over and over again, we saw that these 2 points ended up at the exact same location. That's good, because that's where the graphs are going to intersect. That's my solution. All right, well, that solution here is 4 on the x-axis, and what turns out to be 104 on the y-axis. So we're pondering here a solution of 4, 104. We think that's the solution to the system of linear equations. In this particular question, since we know what x and y are about, let me go and clean off those x's and y's that we wrote. Right. This was a time, x. This was distance, y. Right. That means 4 hours in, these boats will both be 104 nautical miles out. Well, how do we test that? Well, it's real simple. All right. This was my x. This was my y. So what I'm going to do in both equations is change x into 4 and y into 104 and make sure that the left side equals the right side. Again, that's what should happen here. The left side should be the same as the right side in both equations. It could happen in one, absolutely, with anything pretty much. All right, we can plug in 2 and see what the y is, but it's got to work in both equations. And that's what they're showing you down here at the bottom of the presentation. All right, when I change this one into 4 and 104, I get 16 times 4 plus 40, which is 104. The other side says 104. We've got to check. The left side is the same as the right side. In the other equation, the 26x plus 0, when I change this into 4 and this into 104, I get 26 times 4. If you want to say plus 0, you can. It's 104. The other side says 104. Equation checks. Since they both worked out to be true statements, that's the solution to the system of linear equations. All right? In context for this particular question, again, that means 4 hours out. The boats will both be at the same point. They're both going to be 104 nautical miles out. All right, let's go ahead and take a look at number 2. Now, in number 2 here, what's different? Story problem's gone. All right, they're just telling me to solve each linear system by graphing, and then I'm supposed to check my answer here. Now, they've given us a couple of different equations here, which is obvious, but what I really mean here is equations written in different forms. All right, so the first one there is written in slope-intercept form. Y equals 2x minus 7. So when it's written in slope-intercept form, as we did when we covered the section with slope-intercept form, the first thing we do is look at what's at the end here. It says minus 7. That means the y-intercept of this graph is at negative 7. So on the y-axis, I would put a dot at negative 7, which is down here. All right, and then my slope here is 2. Well, that means it's actually 2 over 1, because remember, you always want to write slope as a fraction. 2 over 1 means I'm going to rise 2 and run 1. So from this point, I'm going to rise 2 and go to the right 1. And again, I can do that over and over and over again, which might help me establishing really clearly where this graph is going to go. So I'm at negative 7. All right, I go up 2, which puts me at negative 5, and I go right 1, which puts me right here. Now I'm on the graph. All right, I'm going to keep going up 2 and right 1 over and over and over again. So now I'm going to go up 2, right another 1. That's this point right here. Up 2, right another 1. That's this point right here. Up 2, right another 1. That's this point right there. All right. Hopefully what will happen, you already know what's going to happen because you see it on the screen. Hopefully what's going to happen is my other line is going to go through one of those points, and then I don't have to make any guesses here. Okay. 3x plus y equals 3. Now that's written in standard form. And when we did standard form, that's when we did the intercepts method. The intercepts method says, we say, okay, x is 0, find a y value, and then let y equal 0, find an x value. The x value is where the graph goes across the x-axis. The y value goes where the graph goes across the y-axis. That's an option for us here. What I want to do instead, and what they're showing you right here, is they decided to rearrange this equation. Change this equation into slope-intercept form, which is something else you've already done this year. Well, if I want to write it in y equals mx plus b form, that's exactly what they're doing. All right, that means y has to be all by itself on the left side of the equal sign. That means that 3x has got to move. And the way I move that 3x is to do the opposite. Since 3x here is positive, the opposite of a positive is a negative, and I'm going to subtract 3x from both sides. So that would be y equals 3 minus 3x. Now, problem is that that's not in form, because in form here, proper form, the X thing is the first thing after the equal sign. So what I want to do now here is flip the floppity-floop. All right, I'm going to flip the right side around so that X thing is first. Now when I do that, I have to preserve what I have there. If I cover that up, it says negative 3x. When I flip it around, it still has to say negative 3x. And that's how I come up with y equals negative 3x plus 3. Same thing for the 3. 3 was positive there. When I bring it down here, it's still positive. That's how they came up with this guy. Let's graph that now. So y-intercept number is 3. So it goes across the y-axis here at 3. Slope here says negative 3. Remember, we're going to treat that as a fraction, so negative 3 over 1. So that means from this point, I'm going to go down 3 and right 1. Put a point. Down 3 again, right another one. Put another point. Well, I can stop, because now when I connect those points, you can see I have an overlap point. Again, this overlap point is my solution to the system of linear equations. All right, where is this point of intersection? Well, it's at 2 on the x-axis and negative 3 on the y-axis. So the solution here is 2 comma negative 3. Again, what does that mean? That means in both of these equations, if I change x into 2 and y into negative 3, the left side will be the same as the right side, which is what you can see they're showing you down here. Change x into 2, y into negative 3. 2 times 2 is 4, minus 7 is negative 3. The other side says negative 3. Here, all right, I'm going to change x into 2, y into negative 3. 3 times 2 is 6, plus negative 3 is 3. The other side says 3. There you go. You solved the system of linear equations. This is really a very serious algebra concept, something you will do in algebra class. So if you've mastered this now, you're going to be that much further ahead. All right, let's go on and go ahead and take a look at the concluding example here. Or the concluding examples, rather. Number 1 says a bus leaves the school traveling west at 50 miles an hour. After it travels 15 miles, a car follows the bus traveling at 55 miles per hour. After how many hours will the car catch up with the bus? So, let's start with the bus. The bus takes off, and before we know it, the bus has gone 15 miles. And then what they tell us is that that bus is traveling 50 miles per hour. So we've got to add that onto the expression. So let's just say it traveled 1 hour. At 50 miles an hour, how much further would it have gone? Well, if you're screaming at the screen 50 more miles, you're paying attention. All right? It's already gone 15. Now it would have gone 50 more. So it would now be a total of 65 miles out. Let's try it again. Let's say the bus travels 2 more hours, all right, instead of 1, 2 hours, all right, 50 miles an hour. How far has the bus gone? Well, 50 miles each hour, 2 hours means it's gone 100 miles, plus the 15 it's already traveled means it's out 115 miles, all right. Well, instead of 1 hour or 2 hours, we don't know how many hours. So we're going to write that as 50 times our distance, or rather our time, which we're going to write as x. All right, our car. Now, once the bus gets 15 miles out, the car starts. The car is traveling 55 miles per hour. So at 1 hour out, how far along is the car? 55 miles. It's going 55 miles an hour. At 2 hours out, how far along is the car? Well, if you're screaming 110 right now, you're right. You did 55 times 2. Problem is we don't know the time. So instead of 1 or 2, it's going to be 55 times x. Again, x is representing our time. And that's going to equal y. All right. So now we're going to talk about solving this system of equations here. How do we do this? Well, we're going to do this by graphing. All right. I'm going to flip this one around, because when I flip that one around, it'll be in slope-intercept form, which I know how to graph. This one is almost in slope-intercept form here, all right, but I'm going to add a plus 0 just like I did earlier, because remember, adding 0 doesn't change the equation, but what it does is it gives me something that's in proper slope-intercept form. All right, so I'm going to sketch myself a little graph, and I'm going to chop off the quadrants over here on the left, 2 and 3, because I don't need them. All right, and I could really chop off this one down here if I wanted to, but no big deal. So 50x plus 15 for the bus. So I'm going to go up to 15 to start on the y-axis. And then my slope here is 50, or 50 over 1, because remember, slope is always a fraction. So slope of 50 over 1, remember that means I'm going to rise 50 and run 1. And I can do that over and over and over again. So from this point, I'm going to go up 50 and right 1. Now I'm not going to be real precise here, but if I go up 50, I'm at 65, and then I go over 1, I'm at 65, comma 1. All right, I'm going to go up 50 and right 1 again. All right, when I do that again here, all right, I'm going to be over at 2 now. My x-coordinate, adding another 50, that should give me 115. Let's do it again. Go up another 50 and right another 1. When I go up 50 here, I'm at 165. Right another 1 puts me at 3. Let's try it one more time. I'm going to go up another 50 and right another 1. When I go up another 50, I'm at 215. Right another 1 puts me at 4. So 4 hours out, I've gone 215 miles on the bus. Boy, does that sound like a disaster. All right, so got our equation. We could graph it. Let's get the car. Car is going 55x plus 0. So it's going to start here at 0. And I'll change color so we can remember what's what here. I'll go ahead and change the car into red. Starts at 0. 1 hour in, it's going to be at the 55-mile marker. All right, because I'm going up 55 and right 1. So I go up 55 and right 1. I'm at 55, comma 1. All right, when I go over another 1 hour here, I'm going to add another 55 to that, because again, I'm going up 55 and right 1. When I do that here, that's going to give me 110, comma 2. Well, that's interesting. I'm getting pretty close here. All right, next jump, I'm going to go up another 55 and right another 1. Well, when I do that, lo and behold, I'm at 165, comma 3. Well, that's a point I already had, which is why I wrote it on top of that one. All right, I can connect those points, but we did it with values here, numeric values, and I know the point of intersection now is 165, comma 3. Well, that answers my question. All right, the buses are going to catch up to each other 165 miles out, and at that point in time, that means they're going to be 3 hours out from their original destination, which is why the solution there says 3 hours. All right, let's try this one more time with number 2 here. We're solving the linear system by graphing here, and we're supposed to then check our answer. No big deal, we've seen how to check our answers. So this first one here is already in slope-intercept form, so I want to graph that one with slope-intercept form. The second one here is not in slope-intercept form, but I'm going to go ahead and change it to slope-intercept form. Again, we could do the standard form of graphing. Standard form of graphing says find the x-intercept when y equals 0 and find the y-intercept when x equals 0. We can do that, it'll work. Right, but I would rather do the slope over and over and over again and hope I get a point of intersection. Hint, hint, you're probably going to. All right, so let's rearrange here. I'm going to knock 5x off both sides. And when I do that, I'm going to have y equals -1 minus 5x. Problem, that's not slope-intercept form, because slope-intercept form has the x first. So I need to go ahead and flip this around, and that's exactly what I'm going to do. So I'm going to rewrite this as y equals -5x minus 1. That's slope-intercept form. That's where I need to go here. All right, so let's go ahead and graph these, and we'll try and be as neat as we can and hope we find a point of intersection. So first one is y equals negative 4x plus 1. Remember, when I do slope-intercept form, I always plot this number at the end first. That's my y-intercept, where the graph goes over the y-axis. 1. My slope here is negative 4. Slope of negative 4 means I'm going to go down 4 and right 1. And I'm going to do that over and over and over again. So in this particular question, I'm going to go down 4, 2, 3, 4, and right 1. All right, well, that puts me, as you can see, at 1 comma negative 3. All right, let's do it again. Let's go down another 4 and right another 1. And as you can see, that puts me at 2 comma negative 7. There's my line. All right, let's try the other one. Y equals negative 5x minus 1. So the first thing it says I'm going to do here is I'm going to go down 1 and put a dot. All right, again, that's from the y-intercept, which is always this number at the end. Then my slope here says I'm going to go down 5 and right 1. Remember, that's what a slope of negative 5 means. Slope is always rise over run. So I've got a rise of negative 5 and a run of 1. So from this point, I'm going to go 1, 2, 3, 4, 5 down, 1 over. Put a point. I'm going to do it again. I'm going to go another 5 down and another 1 over. And as you can see, what's happening here, as I connect my points, right, they're actually getting further apart. The point of intersection actually works out to be way up here. Right, so how are we going to figure that out? Well, we're going to do something we haven't done yet. I know that's dangerous, but we're going to reverse the ideas of slope here, and hopefully that'll help us identify our points of intersection. So let's go back to this first equation here. Negative 4x was the slope. Negative 4, rather, was the slope. Remember, what that meant before was I was going down 4 and right 1. Well, I can reverse it to come up with this line. That also means I can go up 4 and left 1. So if I go up 4 and left 1, I have a point there. Right? And that point here is at negative 1 on the x and 5 on the y. I can do it again if I need to. In this particular case, go up another 4 and left another 1. And that means I'm at negative 2 comma 9. Right? If you have a hard time visualizing it, think about it with the line we've already drawn. It's got to make sense. All right, 4 and 1, right? I'm not going 4 left because that would make the line go way over here. I'm going up 4 and left 1. Notice I'm right on top of where I should be. If I go up another 4 and left 1, I'm right again where I should be. Let's do the same thing with the other equation. Right, this other line here, all right, I'm going to go the other way here. All right, I'm going to jump 5 up and 1 to the left, because again, that's going to make it match this line. 1, 2, 3, 4, 5, 1 up. All right, I'm going to do it again. 1, 2, 3, 4, 5, and 1 over. Bingo! All right, I found my point finally. They match up here at negative 2 comma 9. We have to reverse the idea of the slope as we know it. But we did come up with that point. Negative 2 comma 9 is the point of intersection. Again, if you draw yourself a really nice, neat graph, as I talked about in the introduction, big enough graph here, you'd have to go out to tens. But if you draw yourself a really nice, neat graph, and use a straight edge, and just plot these 3 points here and these 3 points over here like we did, and connect your points out, you won't have to do all that work. All right, you'll see with your neat lines there exactly that point of intersection at negative 2, 9. You won't have to reverse the slope. Bingo, bango, that's your solution. As far as checking it, remember, what does my solution mean? My solution is the value that works for x and y in both equations here. It works in both at the exact same time. So when I check it here, I do negative 4 times negative 2, negative 8, plus 1 here, negative 8, I'm sorry, positive 8, negative 4 times negative 2 is positive 8, plus 1 is 9. Well, y is supposed to be 9. Perfect. This one here, 5 times negative 2, my x, negative 10, plus my y value 9 is how I get to negative 1. Checks. X and y in both situations here make a valid solution for both equations here. That means we've solved the system of equations.